Okay, so today we are going to do what should be a foldable for us for graphing rationals, but those are a little bit difficult to do when I can't give you paper. So I did my best to create a digital foldable. So I know that some of you really prefer to print things out and do your notes on paper and then, upload them that way, and I totally respect that, but I'm asking that today you please try Kami, because there are links embedded into this, and I'm not going to lie, I'm kind of proud of myself. So we're going to do my digital foldable. So this is called PPD Rady, or sometimes people say RAT2EY, but I like Rady better. And all of the blue letters in this foldable are links to their respective pages. And so once you have your select tool, you can't have the pen or anything, but we can click, and yes, you could scroll through this too, but let's say we start with PPD, we'll get to what that means, and then say, okay, well then I could go back home, so now I'm at the home page. Let's see what A is, so here's the A page, but we skipped R, so we could go back to R. So even the blue letters up here and the blue letters in here, they are all links to those pages, so it's kind of like being able to flip through a foldable, and this is the acronym that will help us. So sometimes when we're graphing rationals, we will have like lists of things that you need to fill in to be able to do what you need to do to graph. But if it's not there and you can write PPD Rady at the top of your paper, then you will make sure you get all the pieces that you need. All right, so we are going to start with the PPD. All right, so I need to select PPD. My drawing. All right, so the P in the PPD stands for parent. Okay, so we want to know, does my function have a parent? Right. Talking like parent functions, obviously. So if I have a parent function, then I could just do transformations. So the parent functions I have to choose from would be f of x equals 1 over x, or f of x equals 1 over x squared. So either the reciprocal or the reciprocal squared function, which if you remember, we just did these, and they look like this. Reciprocal function would basically be this. Reciprocal squared would basically be this. You have to be careful because sometimes you may assume that it is a parent function and it has, it's just doing the transformations, but sometimes that's not the case, especially if I also have variables in the numerator, or it's not just that one term in the denominator. So it's kind of, even though this is part of it, so I want to discuss it, and I want you to know you can still do some rationals by just using transformations. We are really going to focus on doing them differently, and even if I did the rest of what I'm going to do on all the other rationals with these, I would still get an appropriate answer, so it's fine. Okay, then so the PD part of that, not new to us, we've talked about it a few times. This is our point discontinuity. Which of course would mean that we would have a hole or two. We could have more than one hole. So to know if we have the holes in our function, then we look for factors, a factor or factors that containing x that is common to the numerator and denominator. So a factor of factors containing x that is common to the numerator and denominator, meaning we would be able to cancel it out, and that's where our holes come from, right? So that's what the first thing we have to do. We have to do that before we do the rest of it, okay? So I'm going to go select my select tool. We just did PPD, so I'm going to click on R. And the R stands for roots. Oh, goodness. So I want you to think of the other words that we know for roots. They kind of come up in the description here. So our roots are the x-intercepts, which are the zeros of the numerator. So they are the zeros of the whole function, but when you think about the fact that you have factors in the numerator and denominator, the zeros of the numerator are the actual zeros of the function. And then when do we find those? We find them after reducing. Okay? That's why in the acronym it comes after the PD. Okay? If you do them before you reduce, then you're going to get false answers because you can't be a point discontinuity and a root at the same time. Okay? So point discontinuity first, then roots. So then we're going to move on to the A. A stands for asymptotes. And the A in radi is just for the vertical asymptotes. We'll get to the other ones shortly. Okay? Vertical asymptotes. So the way we find these is if we have a unique factor containing x in the denominator. Okay? Unique meaning that, again, it's done after reducing. So if I'm able to cancel it out with something in the numerator, it is not unique. So after I've canceled everything out I can, then whatever's left is unique to wherever it is. And what asymptotes are lines, a line or lines, determined by the zeros of the denominator. So the zeros of the numerator gives us our roots. The zeros of the denominator gives us our vertical asymptotes, just vertical asymptotes. Okay. So let's move on to the T. This is double T, T squared. Okay, because there's two T's here. We have the first one being tangency, and the second one being togetherness. So we're familiar with tangency when we're graphing. Might not be familiar with the togetherness just yet. So it says, do any factors of R or A have a blank? Okay, so what was R? R was the roots, right? We were on T. What was A? A were the asymptotes. We were on T. So you can jump around like that. So the R is roots. A is our vertical asymptotes. Okay, and basically numerator and denominator, right? The roots come from the numerator, asymptotes come from the denominator. So do any of them have an even exponent? Even, like this 2 here and this 2 here. So the numerator, if I have this squared, okay, just like we had for polynomials, then this gives me tangency. If I have a factor that has an even exponent in the denominator, that gives me togetherness. Okay, so what does that mean and what do these look like? Well, to do tangency, I'm going to draw 2 little x and y axes here. Okay, and then we know that the tangency is still the bounce. So if I come and I can bounce from above, or I can bounce from below, and obviously that's not the whole function. We don't know what else is going on with whatever. Okay, but that's tangency. It's still a bounce. Okay, my togetherness, we're going to draw 3 little x and y axes here. togetherness has to do with the asymptotes. So we're also going to sketch in vertical asymptote, like so. Okay. Actually, I am unhappy with this one, so let me. Oh, it took away my line too, of course. Okay, I don't know if that's any better or not. All right, so the togetherness has to do with what's happening on either side of the asymptote. So on the left side of the asymptote, if I'm approaching infinity, and again, I don't know what's going on after that, or before that rather. Sorry, I meant to make that dotted. Then on the other side, if I have togetherness, then they're approaching the same. They're both approaching infinity on either side of that. Or possibly I could be approaching negative infinity on both sides. And again, oops, well, it won't be that, but you know, who knows what else is going on with that. But this is togetherness, because they're together in the direction that they're going. What it's not is mostly what we've seen so far is where they're opposite. Okay, so this is a big fat no. Okay, that's not togetherness. So this tells me, like, if my asymptote was at x equals 3, and this is squared, then we'll talk about whether it's up, up, or down, down, you know, later on. But I know I would have togetherness at the very least. All right. So the t squared, tangency, and togetherness. So let's review real quick. We've got, is it apparent? Not really going to worry about that. Our point discontinuity, we know how to find that. Our roots, vertical asymptotes, tangency and togetherness, and now, oh, what happened? There we go. I don't even know what I did, but here we are at end behavior. Okay, E is for end behavior. And those are our other asymptotes, our horizontal and slant. So horizontal asymptote, HA, slant asymptote, SA. So with my horizontal asymptote, remember you can be top heavy, bottom heavy, or tied in degree. If it's top heavy, as far as horizontal asymptotes go, this is none. And it opens the door for a slant asymptote. Okay, so top heavy, horizontal asymptote would be none, opens the door for a slant asymptote. If it's bottom heavy, there's no work, y equals 0. If the numerator and denominator are tied in degree, then y equals the ratio of the leading coefficients of the numerator and denominator. Okay, so again, if I'm top heavy and I don't have a horizontal asymptote, then I could possibly have a slant asymptote. If I'm bottom heavy or tied in degree, then I do have a horizontal asymptote, which means there's no way I can have a slant asymptote because I can't have both. Okay, so now let's look at the slant asymptote. If it's top heavy, it opens the door, but remember that the degree of the numerator can only be one more than the degree of the denominator. And so when that happens, to find it, we divide. We will always get a remainder. Remember, you always get it or something else isn't right here. We divide and then we just ignore that remainder. We don't need it for our asymptote. And remember, slant asymptotes, another word for that is oblique. Okay? So, end behavior. Remember, so we've got these two asymptotes. Those are in behavior. The vertical asymptote deals more with middle behavior. This is talking at the ends. And we can cross these, but at the ends we'll be, approaching whatever they happen to be. All right, so then our last letter in RAT2EY is Y. What do I keep doing? I must be hitting it weird with my pen. Okay, I don't know. All right, so this Y stands for Y-intercept. Okay, and you're only going to have one of those. To find that, we do it the exact same way you've been doing it forever. You substitute 0 in for x and solve for y. And because it's a y-intercept, it is always written as an ordered pair. Okay? So there's your y. So let's go through this again. We can go select, we can go home. Right? And then PPD. It's our parent, which again is not a huge focus for us. Point discontinuity. This definitely is. We're going to have to factor, see if we have factors that contain x that are common to the numerator and denominator. Then R. Those are my roots. I need to find those. And they are found after reducing. A. Asymptotes, our vertical asymptotes. We know how to find them. We need to figure out if we have what we have for that. T. Tangency and togetherness. Okay, so the togetherness is the new part. Tangency is an old part. Okay, even though we hadn't done them with rational functions yet, but tangency and togetherness, we're also going to look at sign charts that are going to help us with that. E is our in behavior. We know how to find asymptotes. And then Y for my y-intercept. Okay, so I decided this was going to be it for the notes today. We were going to do like an intro to graphing, but I think I would rather do that with you live. So if you have this much done, at least we've talked through this part. We'll go over it quickly tomorrow, so if you have any questions on it or whatever, you can let me know, but you can go ahead and click turn in on this to turn this in and save it, and then we can open it back up. We'll also talk a little bit tomorrow about how to easily get back to these things. I'm not sure if you even know. You don't have to go through Schoology to get there because I want you to be able to use your notes. That's the whole purpose of why we take them. And I'm also working on how to help you get digitally organized. I'll have you do a little something to get yourself organized so you can actually find your notes. Because believe it or not, you're going to want to use some of these. All right? So don't forget to do your discussion question for today and check on the checklist. And I will see you tomorrow.